Vector spaces and subspaces. So last time we looked at the definition of vector space. It's long, right? What is a vector space? It's a set V. It has operations, plus and times, right? It's a vector space when all 10 of these properties hold, right? You have to have that the operations are closed, their addition and scalar multiplication. You have to have that the addition is nice, meaning there's an identity, inverse, commutativity, and associativity, right? Then you have to have that the multiplication is nice, identity and associativity, and you have to have that the addition and multiplication play nicely together. Those are distributive laws. There are two of them, right? So that's why there are 10 total, right? 2 for closure, 4, there we go, 4 for addition being nice, right? 2 for multiplication being nice, and 2 distributive laws. There we go. There's our 10. So that's our 10 vector space properties. Then what we often do is we look for what are called subspaces, right? So that's the next term I want to define. What is a subspace? We have some V that we already know is a vector space, right? Something we've already proven is a vector space. We're already certain of it. So then what is W? W is a subset of V. So this little curved, it looks like less than, but it's a curved less than. That means subset, right? So it just means some collection contained in the other collection. So W is some subset of the objects in V, right? If W is also a vector space, then we say that W is a subspace of V, right? With those same operations, the same plus, and the same times that V uses. So notice here, it requires that we have some V that we already know is a vector space. Well, in the last video, we proved that V equals the plane is a vector space. We already know this is a vector space. So now I want to look for subspaces in that vector space, right? So here's a perfectly good subspace, right? W is the set, I'm going to let W be the set of all x comma y such that y equals negative x. Turns out this is a perfectly good subspace. We haven't proven this yet, but we'll demonstrate it in a second. So you could write this as x comma y such that y equals negative x. You also could write it, that would be sort of a Cartesian equation for W, right? You also could write it this way. You could write it as, you could kind of plug that in for y, write it as x comma negative x, right? Where x is in R, right? And you can leave it that way, or it might look more familiar if you put, t comma negative t, where t is in R, right? When that's sort of like almost like a parametric form for that same line, right? But either any of these are, just slightly different notation for the same set, right? The same subset, right? So V is the whole plane, right? And then W is just the line y equals negative x, right? So there's V, the whole plane, W, just that line, right? So certainly we can see that W is a subset of V because it consists of just one line out of this whole giant plane, right? But now the question is so this is fine. Yes, W is a subset, right? That's easy enough to see. But is W also a vector space in and of itself, right? Well, what do we have to do? Oh, we have to check these 10 properties again, right? So that's because that's what the definition of a vector space is, right? Um, but hang in there because it's not going to be as bad as it was last time. Here's why. There are a few of these properties you really do have to check. So you really have to check 1A. You really have to check 1B. And you really have to check 2A, right? So you have to check that it's closed in their addition. You have to check that it's closed in their scalar multiplication. And you have to check that it has the additive identity. You have to check that the zero vector is in there, right? There's no way around that. It's going to turn out properties 2b through the end. We don't actually have to check 2b through 4b. The other 7 properties, you don't actually have to check. You just have to check those first 3. And here's why. Well, suppose you have, so here, let's actually do 1a, right? So why does 1a work? Well, pick 2 points along that line, right? And add them together. Do you get another point along that line? Yes, absolutely. Basically, because you when you add them together, you can factor the negative out, right? So adding together 2 points of that form produces another point of that form, right? So we're saying that, if you pick one vector along this line W, and you pick another vector along this line W, right? And you add them together, then their sum will again be along this line W, right? So the first one, the first property, closed under addition, is just fine. Also, if you pick some point along W, right, and you multiply it by a real number, does that result still lie in W? Yes, absolutely, because if you start with a point whose x coordinate is the negative of its y coordinate, or vice versa, same property, and you multiply it by a real number, you still get a point whose x coordinate is the negative of its y coordinate, and vice versa. So it preserves that property, right? And no matter whether r is positive, negative, 0, doesn't matter, right? And again, here I should, I'm not being very careful with my variable declarations, right? But I'm, just expressing the key idea here. Um, so don't take what I'm writing as a formal proof. I'm just explaining the key idea. Now, how about 2a? 2a literally just says that it does the 0 vector lie in W. Yeah, sure, right? Because that satisfies this equation, y equals negative x, 0 equals negative 0, right? That's perfectly good. So there is our vector space V, right, with this smaller subspace W living inside it. Why don't I need to check the rest of the properties? Well, 2b, right, kind of follows from the fact that we have closure under scalar multiplication, right? So you can multiply by -1. You could prove that that will always produce additive inverse, right? So that sort of follows from 1b, honestly. But then here's the cool thing: 2c all the way down through 4b. Those, I claim we don't have to check those, right? Because 2c through 4b, they automatically follow from the fact that V is a vector space, right? They follow automatically from that fact. Because say you want to prove that in W, addition is commutative, right? So you want to show, right? Let's think about this property 2c, right? Well, for 2c, if you pick two vectors in W, well, then those vectors are automatically in V, right? Because W is a subset of V. And for all vectors in V, this holds. Addition is commutative. V plus W equals W plus V. So there you go. A commutativity automatically holds in W since it held in V, right? So that's and the same thing goes for all the rest of these properties, right? For 2C, 2D, 3A, 3B, 4A, 4B, right? So they all follow from the fact that V is a vector space, right? So this is extremely convenient. It's often called the subspace theorem, right? This observation. So the subspace theorem just says that if V is a vector space, and W is a subset of V, then W is actually a vector space again, right? It's actually a subspace of V if and only if what? Well, now you just have to argue that addition is closed in W, right? You have to argue that scalar multiplication is closed in W, and you have to argue that the zero vector is in W. And as long as you have those three properties, you can bypass the rest, right? So that massive list suddenly becomes a lot more manageable. As long as you have some parent vector space that this other set is living inside, right? So this is a very, very convenient property. So let's then, of course, you can't use this unless you have some common parent vector spaces, right, to work with. Right? What are things that often get chosen for V, right? So probably the most common one is the one we already discussed. So one common parent vector space is just n-dimensional, right? Real space, right? So what is that? That's just Rn, right? Which is just, if n equals 2, it's the plane. If n equals 3, it's your three-dimensional XYZ coordinate space, right? And so it's in general, it's just taking n, it's just ordered lists of n real numbers, right? So this is a vector space, right? Here's another common parent vector space, right? So it's the set of all functions on a set D, right? So pick some domain, fix some domain D, and then take the set of all functions on D. So this is a perfectly good parent vector space, right? So, and sometimes you'll see it's written almost like a exponential on sets. Because here it's kind of like the domain is almost the numbers 1 through n, because those are the different inputs, and then you're assigning outputs is each vector. So this is sometimes how it's written. But yeah, this is right. So this is all functions f such that f is a function um, with domain D, right? And let's say, and you do actually need to fix a codomain too. Let's say the real numbers um, or that's what the base of that exponential notation means, that your outputs all live in the real numbers. This is maybe not immediately obvious that this is also vector space, but it is. You could check all 10 properties. Um, I'm not going to show checking all 10 properties, but just to indicate quickly what that would look like. If you have, say, one function on a set D, and another function on a set D, right? And you add them together, you get another function on that same set D, right? So for example, let's say that D is the whole real number line, right? Then, if you take, um, say we have a function 2 plus cosine x, right? And we add it to the function sine of x minus 3, right? You get another function. And that function that you get is cosine plus sine minus 1, right? So there's an example of why addition would be closed on that r to the d, right? Or if you take a function and you um, multiply it by some real number, that gives you another function whose domain is the same, right? Still that set D is your domain. You could say that the zero vector is in here, right? The constant function f of x equals 0, right? That is perfectly good element of this set, right? Just map everything in D to 0, right? That's a perfectly good function. And that, if you add it to any other function, it preserves its identity, right? So that's a very common parent vector space, right? Set of all functions on a given domain. In the context of differential equations, that's maybe the most important, or one of the most important, right? Um, so so these are very common parent vector spaces that we work with, right? Um, Now, what would be an example of a subspace, right? So let me look at another on this function vector space, because this is sort of very, very important example. So here is V. Let's say V is the set of all functions that are defined on the whole real number line, right? So V is this massive, massive set, right? So it's a set of all functions defined on the real number line. So you have, one element here is, say, f of x equals x squared, right? There's a function whose domain is the whole real number line, right? And let's say here's another one, would be f of x equals, um, arctan, right? There's a arctan x. There's another perfectly good function on the real number line, right? It's defined on the whole real number, right? And then now this we're by what we argued up here. Now I didn't check all the properties, but you can check all the rest of them. All the other properties, they all just look like the regular rules of algebra, right? Commutative law, associative, distributive, etc., that you do when you do algebra with any sort of function, right? So they all hold, right? This is a perfectly good vector space if you carefully check all those 10 properties. So let's now say, okay, we're given that this is a vector space, right? And then we can ask ourselves this. Let's say W, which is going to be the set of all f, the set of all functions in this V, right? Set of all functions, such that, let's say, f double prime minus f equals 0. Let's ask, is that a vector space, right? So what do we have to check here? Well, we have to show that here's W, right? And W has some things, some functions that are in it, some functions that are not in it, right? So I very purposefully put, x squared outside W in this Venn diagram, because it is not the case that x squared double prime minus x squared equals 0. That's not true, right? I put arctangent outside because it's also not true that the second derivative of arctan minus arctan equals 0. But what would be inside W? Well, you could do characteristic polynomial, right? Let's solve this. So what do you get? You get lambda squared minus 1 equals 0. So you get lambda is plus or minus 1. So what do you get? You get that the general solution is f of x equals c1 e to the x plus c2 e to the minus x, right? So that's what's here in W, is it's all the functions that you can write using different values of c1 and c2, where c1 and c2 can be any real number. So here here's one element of W. So, I could have, say, just e to the x. That's if c1 is 1 and c2 is 0, right? You could have here, so that's one function that's in here. You could have f of x equals, how about 2 e to the x minus e to the minus x, right? There we go. There's that would look, something like this, right? There's another example, right, of a function in there. All right, so now the question is this actually a vector space? Well, let's check just those three properties. Let's apply the subspace theorem, right? To see if it's a subspace of V. It's going to inherit properties 2C through 4B from V. But we do have to check 1A, right? So if you have two functions in W, right? What do you know? Well, you know that they're both of this form. Constant times E plus constant times E to the minus X. Right? Not necessarily for the same constants. So let's call it C1, C2 for F and D1, D2 for G, right? So what would you have then? Their sum, if you add those together, you're going to get what? Well, combined like terms, right? You still get something of the form constant times e to the x plus constant times e to the minus x. And therefore, their sum is still in W, right? So if you add together two elements of W, you end up with another element of W. You can kind of see that here, right? If you add these two elements that I wrote there, what would you get? You'd get 3e to the x minus e to the minus x, which is still a function in W, still of that same form, right? Um, okay, so there we go. So that property of additive closure holds, right? Closure of addition holds. And so does scalar multiplication, right? If you have f is some function in W and you pick some real number, right? Then if you have R, F, X, what is that? Well, F, using that same F that we had up above, you could say that R times C1 e to the X plus C2 e to the minus X, you distribute the R, right? You get R C1 e to the X plus R C2 e to the minus X. Well, that's, again, of that same form, right? That's an element of W. So this is closed under scalar multiplication as well. Lastly, and no less importantly, right, you have 2A. Yes, it is true that the constant function f of x equals 0 is in W because, well, just test it. Plug it into that differential equation, right? 0 double prime minus 0 is 0 minus 0 is 0. So it solves the differential equation that is the membership condition for W, right? So there we go. By the subspace theorem, W is a vector space. It's a subspace of V. You don't have to check all that other stuff. Subspace theorem says as long as you know W is contained in some vector space V, just check the first thing. It's fine. Right? So by the subspace theorem, right, W is again a vector space. There we go. So there's an example of subspace, right, in V. So we proved that something is a vector space by just checking those first three properties instead of all 10, right? That's the beauty of the subspace theorem. So you get to show that something's a vector space without reinventing the wheel, right? You can say these very common vector spaces, like functions on a given domain or n-dimensional real Euclidean space, use the fact that those are already vector spaces, and it will make your life a lot easier when you're looking for new vector spaces living inside those. All right, great, thank you. More adventures with vector spaces soon.